I'm going to be going over capacitors in series and parallel. And this is the equation that we're going to be mainly looking at and deriving other equations from today. So it's that charge is equal to voltage times capacitance. So we're doing in coulombs, this we're doing in volts, and capacitance, which is what we use for capacitors, is in farads, but we usually use microfarads just because farads are really large. And capacitors are electrical components that store charge. So this is what they look like right here. They're just two parallel lines, but we're looking at these plates just right over here. So we have a volt source, and the positive charges are going to be coming in one side and coming out the other side. And it's what goes in and it comes out is the conservation of energy. And charges or capacitances, there's a few things that affect them, and that is the area of the plate and then the distance between the two plates. And so that's this equation right here. And so if you see that we have a large area on the plate, then it'll have a larger capacitance. And if the distance between those capacitors is decreased, then it'll be a larger capacitance. So smaller area between them means larger capacitance, just because the charges can flow easier. So we're going to be looking at series capacitors first. And this is the equation that we use to find the total capacitance in a system. And I'm going to show you how to get that in just a second, but this is what they look like, just one after the other. And then what the charge that's coming in, same charge that's coming out for each of them. So in a series capacitor, the charge is going to be the same throughout each capacitor, which is different from parallel, as I'll explain in just a minute. So I'm going to show you how we get this equation. Is that we know that the voltage is equal to the charge over capacitance, and then we'll use that for each individual capacitor. And since we know that the charge is going to be the same coming in and going out at each one, we can just ignore that. So we know that we can just add up these capacitances, and that will equal the total capacitance. So that's why we take the inverse at the end. And the equations for series and parallel are a little bit different, and sometimes it's hard to get them straight. You might mix them up. So a little mnemonic that might help you is just that in series, C's go under these. In series, C's go under these. So in series, C's go under these. So if that helps you, it helps me remember that just because it rhymes. And then, so we'll do a little practice. So if you have 2 microfarads for the first capacitor and 4 for the second one, then you just get, I'm going to do right over here, 1 over 2 plus 1 over 4. So that's 3/4, we get to take the inverse. So there's 4/3 microfarads. And then for parallel, this is how they look right over here, just in parallel, just as you would with a resistor. And then this is the equation, and it's a lot easier. But unlike series, the charges are not the same throughout each one. They can be different, but the voltage is the same. So this voltage right here is going to be same as this voltage here. So knowing that, then we can just eliminate all these voltages, and we know that it'll just be the addition of each capacitor, and that'll be the total of the system. So we have the same numbers here, 2 and 4, but as 2 plus 4 equal just 6 microfarads. So it's a lot easier than series. And then do a little practice problem here real quick. So you have your volt source feeding in those the charges going in, and then to solve for that, you usually just want to divide it up and look at it as different capacitors. So we'll see if this whole thing is one and this whole thing is another capacitor. So you just do it like that. It's usually easier if you should always do the ones in series first. So with this one, you just get it's like 7 microfarads. And if you want to know the whole charge of this system, then knowing that charge is equal to voltage times capacitance, then we just multiply 7 by 20. So I just 140 coulombs. And sorry, it would be 140 coulombs if these were just farads. So 140 coulombs. Another practice problem, if you want, you can pause and try to work it out on your own. It looks complicated, but you just want to divide them up. So look at this one as one, and then this one is another, this one is another, this one is another. So it's actually not that bad. So just 1 over 5 plus 1 over 4 plus 1 over 5, and then plus 10, because these are parallel to each other. Then same thing for the third one. Then you add them all up, because really, if you simplify it, you're just looking at a bunch of them in parallel when you simplify down the series ones into parallel. So you add them all up, you get 17.8 microfarads. Capacitors are useful in many situations. Lots of our electrical devices use them. For example, a camera. There'll be capacitors that'll store charge, and when you go to take a picture and the flash goes off, those capacitors quickly release that charge, and that's how it works.